Hello everyone, welcome to my presentation of our paper, Model Checking and Collision Avoidance of Nonlinear Autonomous Vehicles. My name is Rong, and this paper is written by me and my supervisors, Christian Siciliano, Edward Eno, and Christian Lundquist, and we are from Medellin University. This presentation is for the FM'21 conference in Beijing. So when you think of autonomous vehicles, what kind of pictures appear in your minds? Something like this maybe? Vehicles that travel harmoniously on road with sensors to detect their distance among each other and Wi-Fi signals to receive the request from the customers. But it may seem too good to be true, right? The fact is, ever since the first autonomous driving car was tested on road, there are accidents involving this kind of systems all the time. So what happened? What makes them so difficult to realize, and what makes it so difficult to guarantee the safety of this kind of systems? In this presentation, we will be looking at two challenges of the reach and void requirement. The reach and void requirement means that the vehicle needs to start from their initial area, which is the blue circle in this picture, and travel safely on the road, which is the green line here. And then it reached their goal area, which is the pink circle. So if the vehicle can follow strictly on the green line, which is the planned path, then it can be guaranteed to be safe, right? But the fact is, the real trajectory have some inevitable deviation from the reference path, and the deviation can cause collision on the way, and it can make the reachability of the final destination a question mark. So the inevitable deviation from the real trajectory to the planned trajectory, what we call it reference trajectory, is called tracking error. This is the first challenge. And even if the tracking errors that do not cause the collision, there are some probably moving or dynamic obstacles that travel towards the autonomous vehicle. And the overlap of their trajectories may end up to a collision also. So you see there are two kind of hazards in the problem. Okay, now what's the limits of the traditional methods like testing and simulation in solving this problem? Quoting the famous saying from Dijkstra, program testing can be used to show the presence of bugs, but never to show their absence, because the dynamic obstacles can appear at any positions or places in the map, and they can travel at any speed to any angle, right? So the accidents can actually happen anywhere, anytime. So there's no amount of testing and simulation that is able to enumerate all the scenarios, right? And formal methods are famous for verifying or proving the correctness of the reach and void requirement. And one branch of the method is called deduction and theorem proving. Due to the time limit, I can only mention one fantastic job done by Andrew Plazer and Stefan Misch and their colleagues who developed Kimura, which is the tool used dynamic logic. And with their tool, you can actually prove the dynamic system can satisfy some requirement, like the reach and void requirement. And their tool have been used in many industrial systems like European train control system and the air traffic collision avoidance system. But in this paper, we will be focusing on another branch of formal methods called model checking. Different from theorem proving, model checking traverses the states of the model to see if the states can satisfy some propositions or temporal logic properties. And one typical model of this technique is hybrid automata. This picture shows the hybrid automata of a car. So there are two discrete locations, stop and move. And at these two locations, we define the changing rates of two continuous variables. They are speed and position. So when the car starts to move, which means it at the location move, the rate or the changing rate of speed is 5, and the rate of position is speed. So it's another variable, right? And this makes the change of the variable nonlinear. That's why we call it nonlinear hybrid automaton. And to verify if the model can satisfy the reach and void requirement, we just need to have a look at the values of the positions, right? But unfortunately, model checking these hybrid models is undecidable. This is shown by many previous works. So what do? We know that in the world of model checking, verifying the hybrid models like hybrid transition systems is undecidable, right? But still, we have some problems that are decidable. So we want to kind of transfer the undecidable problem to a decidable one, so we can solve the problem. Now, the good thing of using hybrid models is that, like I said before, we can get the continuous trajectory of the systems, which are the real trajectories, right? So if somehow we can transfer the continuous trajectory to a discrete time trajectory, whose verification is decidable, then the problem can be solved. And of course, we also need to prove that the reach and void requirement of the continuous trajectory is preserved by the discrete time trajectory. So next, I'm going to show you how do we make the transformation and how do we do the proof. First, let's deal with tracking errors. Like I said before, the tracking errors could possibly cause the collision, right? So if we don't know if how much the deviation from the real trajectory to the reference trajectory is, it's impossible to know if the real trajectory is safe or not. But thanks to the previous work done by Chu Fan and her colleagues, we know that if the tracking errors of the vehicle have a Lyapunov function, they are bounded by a piecewise constant value centered around the reference path. So intuitively speaking, if you look at this picture, the boundaries of the tracking errors form a safe region, which is highlighted as the yellow area in this map. So the real trajectory can never go out of the safe region. And of course, Lyapunov functions, there are plenty of papers describing this concept and how to synthesize Lyapunov functions for dynamical systems. We don't have time to introduce this, so please check these papers. So based on this conclusion, now we propose our first theorem, which transfers the verification of the real trajectory, which is continuous, to the reference trajectory, which is piecewise continuous. So if we translate the theorem 1 into a human language, what we want to do in this theorem is that if the distance from the reference trajectory, which is the green line, to the boundary of the safe region, which is S is less than L. L is the distance from the reference trajectory to the surface of the static obstacle. Then we know that the real trajectory has no chance to go overlapping with the static obstacles, right? This is quite straightforward. And if there's a point in the goal region or goal area, which is called PG, if the distance from PG to the boundary of the goal area is B, and assume B is less than L, so now we just need to prove that, or to verify that, if the reference trajectory can reach PG. If we can prove that, we know the real trajectory can be guaranteed to reach the goal area, right? Which is also quite straightforward. So with this theorem in the map with only static obstacles, now we can only have a look at the reference trajectory, but not the real trajectory. Now the problem is much simpler, right? But in the environment with dynamic obstacles, things becomes a little bit more complex, because even if, as you can see, even if the trajectory of the dynamic obstacle overlap with the trajectory of our autonomous vehicle, the current position of the autonomous vehicle can be quite far away from the dynamic obstacle, which makes the collision unnecessary or unreal. But if they appear at the same time at the same location, of course, collision can happen, right? So how to distinguish these scenarios? And we developed this new concept called safety critical segment. It is an area after and before the current position of the autonomous vehicle. So only within this region, safety is crucial, is critical. And if the dynamic obstacle enter into this safety critical segment, then collision can be happening. So now we only need to look at a part of the reference path, but not the entire reference path. And if this part of the reference path of this autonomous vehicle and the dynamic obstacle are far away from each other, in the sense that their distance is larger than their tracking error boundaries, then the real trajectories are guaranteed to be not overlapping, so they are safe. So in summary, the first theorem just transfer the nonlinear real trajectory to the piecewise continuous reference trajectory. And based on this result, we don't need to have a look at the real trajectories, right? We just need to check the reference trajectories, which is much simpler, but still the verification of the piecewise continuous trajectory by mode checking is still undecidable. So we need to do more work. What we want to do is to transfer the piecewise continuous trajectory to discrete time trajectory by sampling points on the reference path. And now the problem is, can the sampling points really represent the reference path in the problem of rich and void verification? And what should the sampling granularity be so that they are not too big or too small, okay? So that's why we propose Theorem 2. I just extracted 2 points from the theorem in this presentation because of the time limit. So the first point, we say that the sampling granularity epsilon must be less or equals to S divided by the mode of V. And S is the sum of the tracking errors boundaries, and V is the maximum velocity of the dynamic obstacles. So intuitively speaking, if you look at this picture, S represents the largest deviation of these two moving objects in the map from their reference trajectory. And V is the maximum velocity of the dynamic obstacle. So S divided by the mode of V means the minimum time for the dynamic obstacle to get into the safe region of our autonomous vehicle. So if the sampling granularity is larger than this minimum time, then we could possibly miss the point of collision. That's why I need the sampling granularity be less or equals to this minimum time. Very straightforward, right? So the second point of the theorem just goes to the conclusion. If the sampling granularity satisfies condition 1, then we can say that the fact that the discrete time trajectory satisfies the rich and void requirement implies that the reference trajectory can also satisfy the rich and void requirement. And the proof, of course, is in the paper, so please check it. So now we can get rid of the reference trajectory, but only look at the discrete time trajectory, whose verification of model checking is decidable. Okay, in conclusion, by these two theorems, we transfer the non-undecidable verification or model checking of continuous trajectory to the decidable problem of verifying discrete time trajectory. Okay, now we just need to look at how do we model the discrete time trajectory by using Upo-Tamada UTA. These two pictures show the UTA templates of autonomous vehicles. Picture A models the vehicle controller UTA template, and picture B shows the vehicle parameters UTA template. So the instances of the templates of the parameter UTA are the state variables of the vehicles, like the positions, their speeds, their accelerations, so on and so forth. So basically what we do in this model is that at the end of every PM time unit, PM is the sampling period, the controller UTA invoke the parameter UTA so that the parameters are updated. And then the controller UTA continues to make a decision based on different scenarios. And when the vehicle needs to turn, it goes by this edge. When the vehicle needs to go straight forward, it goes by this edge. When the vehicle meets the dynamic obstacle and needs to avoid, it goes by this edge and execute this function called avoid. And I will go into this function later. So you can see this model actually model the discrete movement of the vehicles. So when we actually run this model, we can get the discrete time trajectory of the vehicles. And these two UTA templates are for the dynamic obstacles. The first one is the initializer, which non-deterministically chooses the initial values of the state variables, like the positions, speeds, and heightings of the dynamic obstacle. So by using this template and initializing the dynamic obstacles, we know that the obstacle can actually appear at any positions in the map and start with any speed and any angles. And picture B models the movement of the obstacles. So basically what it does is to change the positions, speeds, and heightings according to the, of course, physical law. And also it non-deterministically chooses the heightings and accelerations of the dynamic obstacles periodically. So every certain time period, the obstacle has to change, has the chance to change its direction and acceleration. So what we want to achieve by using this model is that, okay, if the vehicle, autonomous vehicle model can satisfy the reach and void requirement in the existence of this kind of dynamic obstacles, which can appear at any places, at any time, and travel at any speed, at any direction, then we know that the autonomous vehicle can be safe under any circumstances and can reach their destination, of course. So this picture shows the concrete steps of our method. Initially, we need the nonlinear vehicle models so that we can calculate the tracking error boundaries. And then we build the UTA template that I introduced before. Then we need to configure the parameters like the map size, the vehicle speeds, etc. Then at step 3, we instantiate the UTA models. And next, we check the models in UPO Stratego. So people who are familiar with UPO Stratego may be a little bit confused because this tool is mainly for synthesized controllers. But here we only use it as a model checker because the latest version of UPO Stratego supports calling external libraries, like I showed here. So basically, by using this function, we do not need to write the code of the collision avoidance function in UPO, but by using standard C with C++, which is of course much more powerful, and we just compile it into the regulated format like .dll in Windows or .cso in Linux, and then we can just link it to the tool, and then UPO Stratego can call the external library during the verification. So what it does is that, like here, when the controller UTA goes by this edge and calls this function, avoid, the UPO Stratego calls the external library and pass the status of the model, like the positions or all the other variables of the autonomous vehicle, and also the parameters of the dynamic obstacles and information of the map to the external library. And then the external library just run its method, run its functions and then generates the next movement, next direction, or the next target speed for the autonomous vehicle. And then by using the new information, the controller UTA updates the vehicle parameters so that, okay, in the next sampling period, the autonomous vehicle can actually choose another direction or, decelerate in order to stop and avoid the dynamic obstacle. So this is what we do here. So if the verification returns true, we know that the vehicle can avoid any kinds of dynamic obstacles under any circumstances and reach their destinations. But if the verification is false, we also get the counterexamples which represent the problematic scenarios. And by using these scenarios, we can actually improve the collision avoidance algorithm here. So it's a closed loop. In this paper, we are going to verify a novel collision avoidance algorithm based on depth of flow fields. And what the algorithm does is that it generates two kinds of fields: static flow fields and dynamic dipole fields. If you look at picture A, along the reference path, the static flow fields generate attractive force to draw the vehicle to the reference trajectory and eventually to the destination. It also generates the repulsive force surrounding the static obstacles. So when the vehicle gets close to the static obstacles, they can push them away by using this repulsive force. But if two moving objects, like the dynamic obstacle and the autonomous vehicle, get close to each other, the algorithm generates dynamic dipole fields surrounding them, like two magnets with, of course, opposite dipoles. So if the closer they get to each other, the stronger the force will be to push them away from each other. Right. So now the problem is, if the algorithm can work correctly in all kinds of scenarios. So we verify the algorithm by using our method, and we found actually two problematic scenarios. In the first scenario, the autonomous vehicle, which is the blue dot, they are drawn to the dynamic obstacles, which are the red dots. So ideally, it should be pushed away, but in this particular scenario, they are actually drawn to the dynamic obstacles. Weird. And in the second scenario, we found the Lovelock scenario. We call it Lovelock because when the autonomous vehicle and the dynamic obstacle travel opposite to each other on the same line, they just go back and forth forever. Because the attractive force on the reference path draws the vehicle forward, and the repulsive force generated by the dipole fields then push them away from the dynamic obstacles, and then the attractive force draws them again forward, so they just come back and forth forever. So based on these two problematic scenarios, we improved the algorithm and verified again, and we got a new result. In the scenario with only one dynamic obstacle, the vehicle which is equipped with the algorithm can always satisfy the reach and avoid the requirement. But when the dynamic obstacle becomes two, then the collision inevitably happens. Because we don't stop actually the autonomous vehicle when the collision happens, they can anyhow reach the destination. So the reach requirement is true. But anyhow, we at least prove that the new algorithm can satisfy the reach and avoid requirement when the environment has only one dynamic obstacle. And we leave the improvement of the algorithm for the future work. So in conclusion, in this paper, we propose Theorem 1 and Theorem 2 to prove that the reach and avoid verification of the nonlinear vehicle models, which is undecidable, can be transformed to the verification of the discrete-time models, which is decidable. And the transformation does not lose the completeness of verification. And this is valuable. And in the experiments, we show that our generic approach is able to detect or demonstrate the absence of problematic scenarios. For the future work, we want to use statistic model checking on cases where the distance between the dynamic obstacle and the autonomous vehicles are close, but collisions do not necessarily happen. And we want to explore the approach on more cases like robotic arms or any other kind of systems, dynamical systems. We also want to see if we can introduce more complex kinematic features in our models so that we can deal with more complex cases. Thank you all for listening. And if you have any questions, please contact me via this email. Thank you.